Good morning and welcome to this session on flight mechanics, controls and design with a focus on air. And we have two really good speakers for you. Dr. Aman Chakraborty is in his finishing up his third year in our program and will be speaking first and talking about his lab, the Vehicle Systems Dynamics and Design Laboratory. So Aman, the floor is yours. Thank you.
Thank you, Brian. Good morning to everybody. Thanks for attending, even if it has to be virtually this year. So I'd like to take this opportunity and talk to you a little bit about my lab, the Vehicle Systems Dynamics and Design Lab, and a brief overview of the research that we're currently engaged in. A little bit about me, like Brian said, I've been with Auburn from fall 2018 to the present. I used to be a research engineer at Georgia Tech's Aerospace Department before that. That's where I did my master's and PhD, and I did my bachelor's from India. I'm a private pilot, airplane single engine land, and I'm a member of the Aircraft Design Technical Committee of the AIAA, and also the Modeling and Simulation Technologies Technical Committee of the AIAA. And those are two main facets of the lab's work. My team. So we're a growing lab, currently 3 graduate students. Ashutosh was the first one, then followed by Anthony, then followed by Sarwar. And we've got 2 undergraduate students, Noah and Cameron. Noah is graduating at the end of this semester and coming on board as a graduate student over the summer. So hopefully this growth will continue. So what's in a name? Well, the lab is called Vehicle Systems Dynamics and Design Lab for a reason. Our focus is flight vehicles, both conventional and unconventional, and we also focus on the systems on the vehicles. So systems that enable the vehicle's concept of operations, how to do physics-based sizing of those systems, and analyze the impact on their performance. Then there's dynamics. So the flight dynamics, especially when you're talking about unconventional configurations, what are the stability and control characteristics of those configurations? So we want to be able to analyze and simulate and control those. And then finally, design. We want to look at how all of these things tie into the design and sizing of the vehicle. So the lab's name is very representative of the lab's mission. Here's an overview of externally funded projects we've got going on now, and they're fairly diverse in their scope. We've got funding from NASA Langley and NASA Ames research centers on the flight dynamics and control laws side. Those are active projects. We also have some funding from the United States Air Force as part of the Agility Prime program, which is a kind of a novel program that the Air Force launched, trying to see whether urban air mobility type concepts can have dual use, so both commercial and military applications. So each of these is a phase 1 STTR where Auburn, my lab, is working with a small business concern as part of a SBC plus research institution team tackling each of these research topics. And we'll talk about those in a minute. So as far as flight simulation is concerned, we've kind of geared up to do the following. We've realized that emerging concepts obviously have novel configurations and a lot of aeropropulsive coupling. So we've set up our simulation capabilities to be able to model those types of flight dynamics of novel designs. The flight control systems have to be designed to be very pilot friendly, and it's a concept that's formally known as simplified vehicle operations, or SVO. And we've set up our sims so that we can test different flight control laws and schemes that go towards SVO. And part of that is being able to test different types of inceptors. How does the pilot put control inputs into the vehicle, different types of cockpit displays? How does the pilot glean information about the state of the vehicle, and within the context of SVO? And finally, we want to use that to evaluate how quickly non-pilots or people with limited piloting experience can transition into operating these next generation simplified flight vehicles. We have operational or working towards becoming operational 3 flight simulators. The first one that you see on the left is called the Reconfigurable Flight Simulator. That was the first one that was set up in late 2019. And currently we're upgrading it. We're in the process of upgrading it to be even better. The one you see in the center is based off a decommissioned or non-airworthy Cessna 152 airframe that was donated to us. So we parked it at the center of a cylindrical screen, 18 feet in diameter, that's going to show the external visuals. And we're working really fast to get this operational over the summer. The third one, SIM3, that you see on the right, is already operational, and it's based on a Diamond DA40 cabin section. And it sits at the center of a 270-degree field of view cylindrical screen. So long-term plans for all of these simulation facilities is obviously we want to network them together. And we want to network them within a virtual urban air mobility operational scenario, where these different simulators are all representing different UAM vehicle concepts that are in an urban environment where they're being controlled by a controller station. And then there's a scenario manager that can inject various uncertainties or various unpredictable operational events into the simulations. So that's a long-term goal once all of these simulators become active. So just to give you an idea of what the simulators are like, I've emitted a video which we shot recently that's basically me doing a walk around, and I thought it might be informative.
CL simulator number 3, or SIM3 as we call it. I'm just going to walk you through the setup of our simulator. So this is the operator station or the instructor station, however you want to call it. And this is where we have a couple of the computers that make up the simulator. So this computer over here is the master computer. So our simulation software, MADCAS, and whatever we're using to control the MADCAS resides and runs on this computer. These two computers over here are the image generation computers, and they drive the overhead projectors that show the alpha window view inside the simulator. So we'll look at that in a minute. Okay, so now moving inside the simulator, as you can see, the external visuals are projected on a 16-foot diameter, 270-degree field of view cylindrical screen. That screen is illuminated by 5 overhead projectors, and the 2 image generation computers that you saw back there are responsible for controlling those 5 projectors. We use a special warp and blend software to seamlessly blend the image over the cylindrical screen. SIM3 uses a cockpit that is based on a Diamond DA40, so this was a non-airworthy Diamond DA40 airframe that was donated to us. So the cockpit, the cabin section, and we basically repurposed that for this simulator. There's one more computer over here. This is the displays and controls computer. This is responsible for driving the cockpit displays, for capturing in-temperature inputs from inside the cockpit, and also generates audio. We have full flexibility over the nature and appearance of the displays, over what is displayed and how the pilot can interact with those displays. We have full control over what the in-temperature inputs map to. So they're just collected from here as normalized in-temperature inputs, and depending on what control laws we've got, we have great freedom to decide how those control inputs interact with the aircraft flight control architecture.
Oh, he's just showing the simulation going on.
That's right, and we're really proud of it. Okay, so moving on, now that you got a little snippet of what the simulator looks like, let's just do a quick overview of some of the projects we've got ongoing. Some of them use this simulator. The first project that the lab got started on is funded by NASA Langley out of the Transformational Tools and Technologies project. It's a 3-year project. We're currently in the 3rd year. And the goal was basically to develop tools and methods and methodologies that allow engineers and analysts to look at the flight dynamics and stability and control characteristics of unconventional configurations. And this project has resulted in the development of a tool called MADCAS, and that stands for Modular Aircraft Dynamics and Control Algorithm Simulation Platform. So it's a MATLAB Simulink-based tool, and once we developed it to a point, we realized that even though it wasn't part of the NASA requirements, we could actually use that tool to drive our simulation. So what you saw in the video is actually the tool that we developed out of that NASA project, basically driving our simulator. And we've got some publications in the AIAA that talk about the simulator and the projects we've done using it. A second project that we got is funded by NASA Ames, and it's an STTR project, and both of these are in collaboration with Research in Flight, which is kind of lab's strategic partner. This is a 1-year phase 1 project, and then a 2-year phase 2 project, and the goals for this are to develop analysis and simulation capabilities for gust encounters and gust load alleviation, specifically for distributed electric propulsion, urban air mobility type of concepts. So we just kicked off the phase 2 of this project, and so far we've developed a tool called CLASP, which stands for Controls and Load Alleviation Simulation Platform, and we used it to demonstrate that we were able to analyze gust encounters for a DEP UAM vehicle. This is NASA's LA-8 concept. So this is a class-driven simulation. We've got a simplified structural dynamics model in there. So the structure actually flexes when it hits the encounters gusts or turbulence. So we have full control over what the gust field looks like. It could be symmetric, asymmetric. It could even be continuous turbulence of different intensities. And phase 2 of the project is going to focus on extending the capabilities we developed as part of phase 1 to also be valid for vertical flight mode. So a lot of these vehicles, you see the cool videos where they're going to, concept videos where they're going to take off from a vertiport in an urban area. There are some pretty urban area specific wind patterns over there that these vehicles will have to contend with when they're in a hover situation, which is a particularly vulnerable situation where control authority is a lot lower and the vehicle is close to the ground. So the phase 2 will focus on assessing those with this framework. As I mentioned, we have a bunch of projects funded by the United States Air Force out of the Agility Prime program, and one of them is with Transcend Air. Transcend Air is a startup that is developing and has won several awards for this particular design, which is the VI 400. It is a tilt-wing aircraft, which is capable of airplane-like pretty high speeds, as well as great lifting power in vertical flight mode. The video that you saw over there was actually us simulating the flight model of Transcend's aircraft within our simulator, and that's kind of a part of the scope of this project, to be able to develop and demonstrate the flight control laws that allow simplified vehicle operations and also nap of the earth flying for this concept. Another STTR we have out of Agility Prime is with a Huntsville-based company called Avolution. And Avolution, which is founded by Mark Spencer, a graduate of Auburn University, they have this extensible flight system software that replaces a lot of outdated avionics on aircraft. It's found its way onto several experimentals already, and they're doing work with some of the UAM companies. The scope of this project is to see whether that same software can be incorporated within the systems architecture of our simulator and used to further develop the SVO concept of operations for one of the flight dynamics models that we have in our lab. Another really interesting project is with another startup based in California called MetroHub. And MetroHub has this cool aircraft design where it has extremely novel landing gear that allows it to take off and land in very short distances. So let me just move forward and see. So the gear actually is capable of great range of motion, and the aircraft does precision takeoffs and landings by coming in over the landing surface and waiting for the gear to basically move down and kind of capture or grab onto the landing surface. So obviously that's a pretty complicated simulation problem, and our role in that project is to develop the gear dynamics models and the flight dynamics of the aircraft, as well as the flight control laws that would allow basically automated takeoff and landing operations in a precise manner over a very short takeoff and landing field length. So we're using Simulator 2 once it comes online in order to demonstrate and simulate this particular concept. Now, moving a little bit to the aircraft sizing part, we have a project with DAR Corporation, Design Analysis and Research Corporation, which is actually the corporation founded by Jan Roscoe, who's of course the aircraft design guru that everybody knows about in our field. And we're going to analyze this dual-purpose ducted fan-powered VTOL vehicle that will have two configurations that differ in where the payload/cargo is located. So there's one variant that's going to be personnel transport and UAM, and another variant that's going to be a cargo transport. So our role in this project is to use some of our vehicle sizing and performance analysis capabilities in order to determine the size and the weight and the power requirements of an aircraft like this when it's sized to a certain set of mission requirements. We have a project with Research in Flight and Flugauto, and this project is aimed at analyzing an unmanned delivery drone originally and seeing whether that can be extended to a passenger carrying application. And once again, we're responsible for sizing studies as well as simulation and flight control laws for this concept. And finally, last project from Agility Prime with Research in Flight and an airship manufacturer based in Florida called Skyborne Technology is sizing and simulation studies for an electrified airship concept. So once again, we're basically sticking to our core specialties. Now, internal funding, we were very lucky. We got internal funding from Auburn as part of the IGP program that helps kickstart new hire professors research programs, and we used it to develop our sizing tool. We were able to publish a bunch of papers doing sizing studies, and our most recent conference paper got selected as the best aircraft design paper by the AIAA Aircraft Design Technical Committee. So we really appreciate Auburn's support in the IGP program. And also the same IGP program, we have a collaborative project going on with the Aviation Department, which of course has a fantastic flight training program. And as part of this program, we're gathering a lot of flight data from their operations, and we're analyzing it retrospectively to develop safety analysis algorithms. We're also doing some flight tests in their aircraft where we're gathering data from the G1000 systems and using them to calibrate our performance models, and then hopefully use those for safety analyses of aircraft that may not have the G1000 based systems. Anyway, so that's a crash overview of research we've got ongoing at the VSDDL. Thank you very much for your time and attention. And if you have any questions or comments or just want to talk, just feel free to get in touch. I've got the email address down there, and please feel free to check out the lab's website, which is vsddl.com. Thank you very much.
Thank you, Aman. As you can see, he's quite busy. Lots going on, and we're really proud of him. Maybe time for one question before we hand the floor over to Umberto. And Umberto, if you want to get your slide up, please feel free. I know Scott must have a question, but
I was trying to unmute myself here. Iman, great stuff. And of course, that's something I'm involved with. And the virtual reality is really a powerful tool for training. But at some point in the simulation, obviously, if you can integrate, make a hybrid type of simulator that has the tactile functions and the virtual reality, do your models, can they interface pretty easily with some tactile functions?
So some of the tools that we use are able to support VR, but as of now, we don't have any VR capabilities right at this moment. But the gentleman that's going to start presenting right now, Umberto, that's one of his targets. So I look forward to Umberto actually joining us, and then maybe we can do some collaborative research, which does exactly what you said, Scott.
Thank you, Iman.
So I promise I didn't plant Scott's question, but that was the perfect segue from as Iman just indicated. So